Hi students, so we're doing our second part, part 2, in chapter 9, Introduction to T-Tests, or the T-statistic. So we have finished our 4 steps in hypothesis testing using the T-statistic, and so for decisions where we decide to reject a null based on an extreme observed value compared to the critical value, we would want to measure effect size, just like we've done in the previous chapter, chapter 8, where we did hypothesis testing with z-scores and z-distributions. So in many ways, measuring effect size after doing a t-test is very similar to measuring effect size after doing a z-test. The principle is the same. As you can see here, hypothesis testing looks to see if the treatment effect is quote-unquote greater than chance. If the effect is extreme enough in the sampling distribution, that is the null distribution, for us to say, yeah, there is some sort of effect going on here. So that would be considered statistically significant because we're using statistical procedures to determine if the value of the sample mean in the treated sample is extreme enough. However, very small treatment effects can still be considered statistically significant if, for example, the sample size is large enough so that the standard error is smaller. And so the critical values are less extreme, and therefore it would increase your chances of rejecting the null compared to a small sample size. Therefore, in addition to testing for significance statistically, that is rejection of the null, we want to test, once we rejected the null, that is, we wouldn't need to test it if we have failed to reject, the effect size, to measure it actually. So, for this course, we can use the same technique and formula for t-tests as well. Notice the difference here. When we use Cohen's d, it is now the estimated Cohen's d, the estimated effect size, because again, we don't have population parameters. However, we can still do Cohen's d, except this time it's the estimated value. We can figure out the mean difference, that is between the treated sample mean and the population mean, that is the null hypothesis mean, and then the sample standard deviation here. So instead of sigma, we use S. So for, again, Cohen's d for estimated values, we use the mean difference over the sample standard deviation. So here's an example of this. In this slide we see, we've done the t-test, and now we're going to measure the effect size. So again, instead of measuring it in terms of standard error, that is estimated standard error, we want to measure the difference in sample standard deviations. So what that would look like then here is we have the sample mean of 13. And then the mean difference here is, well, between 13 and the population mean of 10. Well, there's 3 points. Then while that might be a larger, more extreme value for a null distribution, in terms of the sample distribution, well, here you got the standard deviation of 3. So a mean difference of 13 from 10, it would be 1 standard deviation away from the population mean. So the effect size here is 1. Another way of measuring effect size is using something called the percentage or proportion of variance explained. That is, instead of comparing mean differences, we are more directly comparing variability. So we're trying to determine how much of the variability we see in the sample is explained by the treatment effect. So the way we do this, and technique we use here, is to compare variability. So here we have the variability accounted for, that is the treatment effect. Here we what we do here is we square the t-statistic, and then we measure also total variability. That is, well, again, squaring the t-statistic, and then adding the degrees of freedom. So when we look at this then, so what I've done, I fixed the r squared as squared, not r2. So when we look at this then, we start with our observed statistic, that is t observed, and our test statistic. So that's what we get in terms of variability, because, well, the test statistic involves factors in standard error. And so we want to see how much of the treatment effect is explained by the treatment. So instead of looking at in terms of mean differences, this one we're looking at variances. So we're comparing between the treatment variance, or the variance that is explained by the treatment, or the variability that is explained by the treatment, with the total variability. That includes just things like individual differences. When I say just, well, it includes things like mainly individual differences, sampling error, and so on. So that's why we include degrees of freedom. As you may notice though, as degrees of freedom increases, that is going to increase the denominator, the bottom half of the fraction, you're going to see a smaller effect, a smaller r squared. So you can think of it this way. The larger the sample that you're going to get, larger the sample size, well, there's more people, right? So if there are more people, if everyone had an equal chance of being selected, well, there's going to be greater room for individual differences based on, more individuals. Having said that though, that's why we have different sort of guidelines for values for what is considered a small, medium, or large effect using this measure. So especially if you have large sample sizes or large degrees of freedom. Again, remember though, the degrees of freedom also affects the critical value as well, but not the test statistic, although it is, influenced by sample size. Having said that, you have your 0.01 for a small effect, 0.09 for a medium effect, and a 0.25 for a large effect. For now, in this course, you'll be asked to simply measure or calculate the proportion of variance explained. So once you have your observed statistic and your degrees of freedom, you can use it to determine, well, how large is the proportion of the variance explained by the treatment effect. So this is a model of what that would look like using distributions. So here you see an A where you have the original scores in the sample, and it would include the treatment effect. So you can see here that the treatment is doing something. It's pulling all the scores higher. Well, when I say all, most of the scores higher, save one that is below the mean. So you can see a definite treatment effect going on here for these scores for sure. Now here, the adjusted scores, what it would look like, if you were to account for a treatment effect and remove it, then you can see, oh, okay, if the experiment was done again but no treatment was done, the same sample, then you might see something that is more spread out. That is accounting for individual differences without the treatment effect. So you see, oh, scores are going to be around the mean instead of clustered in one direction. So two more things are left to do. Actually, one more thing is left to do after we do two measures of effect size, and that is the confidence interval. This is the third technique that we can use to measure effect size. And how confidence interval works is, according to these points, is that you're trying to estimate the population mean from the sample mean. It's kind of in reverse here, in a way. And you'll see this in a minute, where you're basing the assumption that your sample mean should be near the population mean. And so you construct an interval that defines what is near. Again, how the sample mean should be near the population mean based on the estimated standard error. And therefore, the interval you're going to use would help you say, with quote-unquote confidence, how you would confidently estimate where the population mean should be in that interval. And one of the better ways to explain this is with a distribution. So, for example, we have a t-distribution where we have 8 degrees of freedom, so the sample size is 9, and then we find the critical values at a particular interval. Here is 80%. Again, there are guidelines for setting the confidence interval as well, but for now we use 80%. Again, it's very similar to setting the critical region, again using the same degrees of freedom that you got based on the sample, and you would find the critical values the same way. But instead of looking for critical regions, now you're looking for a confidence interval. And you're interested, instead of the tail portions, you're looking at the body portion, the larger bit. Here is 80%, not the 20%, 10 on the left and 10 on the right. So here you see the critical values. Well, for an middle 80% would be plus or minus 1.397 when you're looking at a t-distribution with a degrees of freedom of 8. That is based on a sample size of 9. So once you've determined this, you can reverse the process and calculate the interval. Notice when you do an observed statistic, you can only find one value. That is, well, the t-score. And so this will be your observed statistic, where you have your difference between the sample mean and the population mean divided by the estimated standard error. So this has only one value, one observed value. But for calculating the confidence interval, again, you may recognize this is where, instead of solving for x this time, or m, we are solving for mu. We're trying to figure out, hey, where would this mu be placed at, or how close would the sample mean be compared to the population mean? Well, in solving for mu, then we use algebra and go, okay, well, we multiply the observed statistic with the standard error, and then it'll be plus or minus that for the mean. So the population mean would have a confidence interval depending on what percentage you want, and that will determine your t values, plus or minus t times the standard error, where you have the sample mean plus or minus, well, t times the standard error. So if we go back to our previous example, where let's say we want to find the confidence interval of 80%. So again, let's say we've done the formula and we have the values we need. Well, we figured out the critical value for an 80% confidence interval, and let's say for now the mean is, let's say, 10. The sample mean, that is. So we plug in that 10 plus or minus 1.397, and then the standard error, which we'll have to calculate. But for now, let's just use a simple one. The estimated standard error happens to be 1. So then you would have an interval of either 10 minus 1.397 or 10 plus 1.397. So the upper value is quite easy. And then the lower value would be 8.603. So then you'd have a confidence interval of 8.603 to 11.397, where you would estimate the population mean to be. So here's another point to help us understand the confidence interval. So here are some points for us. In any t-distribution, the values would pile around t equals 0. That is the mean of the t-distribution. So for any value that we know, that is 1 minus alpha, then that would fall in the plus or minus proportion of t in the appropriate degrees of freedom. So for example, if we have a degrees of freedom for 9, this will be a totally different distribution here. And we set our confidence interval. So here we have another distribution with a mean of 0, a t-distribution, and then we have a degrees of freedom of 9, and we want to make sure we write this. And so look for a 90% confidence interval. We know the middle portion is 90%, and then the left and right of this would be 5% each. And for a confidence interval, it's always two-tailed. There's no one-tailed confidence interval. So then you look for the appropriate critical values, and we can check this for ourselves, see if it really is plus or minus 1.833. We go to our table. Again, we can use two tails at 0.1. Well, that's because we're looking for a 90% confidence interval. And if you scroll down to the bottom, you can read, oh, it's 90%. Right here, see? So in this, we can find out what the confidence interval is. So, and what the critical values are. So what we're looking for here is that degrees of freedom for 9 in the 90% confidence interval column. And there you have it, 1.833, plus or minus. So then once we find that critical value, plus or minus 1.833, then we can, once we know what the sample mean is, then we can calculate the actual interval of means. And therefore, after calculating that confidence interval, we can say something like this. And say 90%, we can say with 90% confidence, quote unquote, that a sample mean would correspond to a t-value in that particular interval. So going back to the slide here. So then when we use confidence intervals for estimating the population mean, there's some pointers that can help us. So first we want to make sure we pick an appropriate degree of confidence. Again, the general guidelines would be somewhere pretty high, like 80%, 90%, 95%, or even 99%. And we use the t-distribution table to find the values of t, depending on your degrees of freedom, what that is, and what percentage you're looking for. Again, you'll be basing that on 1 minus the confidence interval, which would be like your alpha. And then you'd find your corresponding t-value. In this case, we had the degrees of freedom for 9 and a 90% confidence interval. Therefore, alpha is at 10% for two tails. And then the corresponding t-value would be plus or minus 1.833. So then we rearrange the equation to solve for the mean, population mean. And so we will work with an interval. And therefore, the resulting interval would be centered around this sample mean. And we can say then, based on this interval, that we are 90% confident, because we set the confidence level at 90%, that the population mean would fall within this interval. And if you're wondering, hey, what percentage should we set the confidence interval? Well, that's a good question. And here are some factors that would affect how large or wide your confidence interval is. Again, confidence interval is a technique, an alternate technique, to measure effect size. So if you want to increase the confidence interval, you are saying that the interval width is larger. You're saying like, oh, the mean could come from a wider width the population mean, that is. That means it could have a larger treatment effect. Whereas if you want to decrease the confidence interval, you're saying the interval width is smaller, so you're, in one way, you're saying the treatment effect is smaller because the confidence interval is smaller. Another factor then is sample size. Again, with larger sample size, you're going to have more individual differences, and you would have a smaller standard error, though, and you would have a smaller confidence interval. Whereas if you use a smaller sample, you're going to get a larger standard error. It's based on how sampling works. You tend to get more extreme values that way, and therefore you would get a larger confidence interval. So taken together, once we've done our t-test, again including all the first 4 steps along with our decision and some measure of effect size, whether it's your Cohen's d, your proportion variance explained that is r squared, or even the confidence interval, and again in your worksheet you'll be asked to do a percentage of the confidence interval based on a percentage confidence. So once you've done those steps, if you have to publish that result in literature, let's say it's a research report or some type of publication, you would be expected to say stuff like this. Whether the test was quote-unquote significant, that is whether you have rejected or failed to reject the null. So if you have rejected the null, then it's considered significant, statistically significant. And if you fail to reject the null based on your statistical evidence, then you'd say, oh, the test is not significant. You would report the t statistic value, including the degrees of freedom. So here the notation reads t, that means because you're using a t-test, the degrees of freedom, that is n minus 1, and then your actual statistic, this is your t observed here. That is not the same as your critical value, however, which you would set in your step 2, where you would go, okay, this test has certain degrees of freedom, whatever that is, n minus 1, and then that's 0, and then you have your, if it was a two-tailed test, you have 2 critical values, and these are t values, critical 1 and critical 2, let's say. And then you would reject in these extreme regions and fail to reject in these less extreme regions. And we also can report the significance level. That is, well, with a more traditional pen and paper way, well, we definitely need the t-statistic because we're calculating that based on our sample data and estimated standard error. You can find the corresponding p observed as close as you can, provided that we have some p observed, but we can say, yeah, it is less than alpha because, well, the t observed is more extreme than your critical value, so it would have a smaller portion anyway. So you don't need to say exactly what p observed is, but it is definitely less than the alpha, so it's more extreme. When you have software that calculates the exact probability, then you would actually say what p observed is equal to. However, remember, in this course, we are not expected to calculate the exact probability because we haven't taught you how to calculate the exact probability. And even if you can find it happen to be able to find it with, a Z table where, many more Z values are given. In your t-test, you're not really going to calculate the exact probability, especially, if it's some non-rounded decimal figure. So if you happen to show that you found some exact probability and it happens to be really extreme or some value, then we would know you haven't actually done the steps we have provided you. At least, especially if you don't show what the t observed is. So keep that in mind. When you do research and you have the software, you could report the exact probability, but reporting that the p observed is less than alpha and reporting that the t observed is more extreme than your critical t value, that's sufficient. Again, just like you can do one-tailed test for z-test, you can also do one-tailed test for t-test as well. Remember, two-tailed tests are more commonly used because we're trying to see if there's a difference. It's also more stringent and more strict because, well, alpha is smaller because it's split into two. Again, we need to pay attention to what the research question asks to help us determine which hypothesis test and whether we use one-tail or two-tail. Again, the steps are the same. It's still the 4 steps, except now it's one-tailed test, and the critical region is just one tail of the t-distribution, not 2. So here would be an example of this. And this is a good practice for us. We got a degrees of freedom that is 8 here. And the critical value here is plus 2.896. And this is a one-tailed test, so alpha is not split in half. So let's figure out what alpha is equal to here at 2.896 positive. So let's find the value 2.896 positive in the row that is degrees of freedom 8. So we got this row here that is degrees of freedom is 8, and then we're looking for 2.896. Okay, we found the value, but right now we can't see what the corresponding alpha is. So if we go back to that table and scroll up. Okay. First we locate 2.896. Degrees of freedom is 8. Good. Okay. We found it. In the column, it says one-tailed test at alpha is equal to 0.01. So alpha is at 1% here. One tail. So you can remember and think back to things like, in a one-tail alpha test, one-tail test, the alpha is going to be twice as large if it was a two-tail test. Because again, two-tail test would have alpha split in half. So to finish off our lessons in chapter 9, let's finish off with some learning checks. Question 3. The result of a hypothesis test is reported as follows. T in brackets 21 equals 2.38. And the P observed here is less than alpha, set at 5%. So based on what is shown in the report, what was the decision that was made and how big was the sample? So your choices are, the null was rejected if the sample size was 21. B, the null was rejected and the sample size was 22. C, the null was not rejected and the sample size was 21. And D, the sample size was 22, and the null was not rejected. Take a moment. You can review in the previous slides if you need to. Figure out what the sample size is based on the degrees of freedom, where that is reported in that line. And what does it mean when the P observed is less than alpha? So if you remember that degrees of freedom is n minus 1, well then the sample size is 1 larger than your degrees of freedom. And when the P observed is less than alpha, the decision is to reject the null. So B would be correct. And we have true-false questions. Now, let's take a look. Sample size has a great influence on the measure of effect size. True or false? And B, when this value of the t-statistic is near 0, the null hypothesis should be rejected. Again, think about what sample size influence here in hypothesis testing versus in measuring effect size. And for B, think about where the t-statistic is in the null distribution when it's close to 0. Remember, t-statistics are location scores. So both of these are false. Sample sizes influences standard error. It even influences sample standard deviation, but it does not affect sample. That does not affect the measure of the effect size. And for B, when the t-statistic is close to 0, that means it's close to the population mean, and therefore the difference is less extreme, and you would more than likely fail to reject the null hypothesis. the closer it is to 0. So that's it then. That's it for chapter 9. You can see a lot of this in terms of t-tests, and particularly the hypothesis testing part in Cohen's D for effect size is based on what we learned in chapter 8. Again, the same 4 steps. Again, the same decisions we could make. Again, the same errors we could make. Again, the same measure for Cohen's D, except for all these things, we're using the estimated standard error, not the real standard error, because we don't know what the population standard deviation is, or we're not given that information. So in terms of outcomes, when you complete this chapter, you should be able to describe when to use the t-statistic instead of the z-score when you do hypothesis testing. That is, well, we don't know what the population standard deviation is, or we might not even know what the mean is. That is the mean for the population. Also, you should be able to perform hypothesis testing using the t-test. Again, the same steps, but again, keeping in mind that you're going to work with degrees of freedom in the family of t distributions. Setting the right critical region, finding the right critical t-value, comparing that with your test statistic, that is also a t-score, using this estimated standard error, and then making a decision from there. If you have made a decision to reject, you should be able to calculate the effect size in a number of ways, including Cohen's D, proportion or percentage of variance explained or accounted for using R squared, and also the confidence interval. Again, each is with its own technique, and each measuring something. So for Cohen's D, you're measuring mean differences. For proportion or percentage of variance explained, you're comparing variance of treatment versus the variability in everything else. That is including everything in addition to the treatment. And then you could also measure effect size by calculating a confidence interval to see where the population mean is expected to be around the sample mean. Again, the larger the interval, the larger you would say the effect would be. So that's it then. Again, these steps would be practiced in your textbook, in the worksheet, and also in your web tutorials. And if you got any questions after doing these things and looking at these resources along with the step-by-step guides, you can ask me at my college email. If you're taking this at Alexander College, you can ask me at my Alexander College email. So make sure you keep practicing step by step. You can do chapters 8 and 9 together. And chapter 10 would also be built on chapters 8 and 9. So the stronger foundation you can build on chapter 8 and chapter 9 respectively, the more easier of a time you're going to have with chapter 10 as well. And the hypothesis testing steps would be built on and built in for the rest of the course, including chapter 12, analysis of variance, and also chapter 14, well, in the textbook that you would read, or at least those 2 chapters, including, again, ANOVA, analysis of variance, and correlation and regression. So again, keep practicing. You can do this. No substitute from actually practicing the questions with the resources that you have. And we'll see you in the next one.